All right, so to start out, just a little bit of review of the trig derivatives. The two main ones you have to know, the derivative of sine is cos, and the derivative of cos is negative sine x. Tan x we'll see pretty frequently. Derivative of tan x is secant squared x. And then our three reciprocal ones we won't see as much, but they will come up this year. Cosecant x is negative cosecant x cotangent x. Secant x is secant x tan x. And cotangent x is equal to negative cosecant squared x. Now, if you don't have those memorized, just keep in mind you're never stuck, because you can always just use your quotient rule. If you have tan x, just rewrite it as sine x over cos x and do your quotient rule. If you have cosecant x, write it as 1 over sine x. Use your quotient rule. Secant, 1 over cos x. Use your quotient rule. And cotangent x, write it as cos x over sine x. Use your quotient rule. So again, if you don't have those ones memorized, you're not stuck. They'll just take you a little bit more time to get the derivative. So we have seen the limit as x approaches 0 of sine x over x is just equal to 1. And we saw it with h's also on the left there when we did the derivatives of sine and cosine. Well, if you have h approaching 0, as long as the term in the denominator matches the term that you're taking the sine of, that in fact will still equal 1. Likewise, in the bottom one, if we have sine 3h over 3h, that will equal 1. So if we had the limit as h approaches 0 of sine of 7h, that will equal 1, provided we have 7h in the denominator as well. And we'll come back to that a little bit later in the video to work with some limits like this. So trig functions can be used to model different things with vibrations, with waves, different elastic motions, anything that is periodic in nature. What we mean by periodic is it keeps repeating over and over and over again. The example we're going to look at is when you have a spring. So we're going to have a vertical spring that's stretched 4 centimeters beyond its natural length, and it's going to be released at t equals 0. Now we are going to define the distance downward as being the positive distance. So here 0 is the natural length, 4 is our centimeters that we are stretching it to. This is our position function at any time t, for cos t. And what we're going to do is we're going to find the velocity and the acceleration functions. Well, s prime, our derivative of our position function, should be our velocity function. So we could use the notation either way. Derivative of 4 cos t, well, remember, don't worry about the 4. Take the derivative of cos t, which is negative sine t, and then multiply the 4 back in, and we'll get negative 4 sine t. So that is our velocity function. To find our acceleration function, just take the derivative of that. So we could do s double prime t, or we could also call it a of t for our acceleration function. Again, forget about the negative 4. Derivative of sine t is cos t. Multiply the negative 4 back in, we get negative 4 cos t. So again, these represent our velocity function and our acceleration function for this spring once we release it. So what's basically happening is it's going to oscillate. Once we release it at positive 4 here, the spring will bounce back and forth between 4 and negative 4 with a period of 2 pi for one complete oscillation. And here's what we have graphically. So our position function is here. That's telling us where it's located in relation to our natural length of 0. This is our velocity function. And then we've got our acceleration function, the -4 cos t. Now, velocity's absolute value is speed, because speed is not a vector. It doesn't have direction. So the absolute value of your velocity, which our velocity function is sine t. Now, the reason it's a +4 sine t is because, again, the absolute value. Well, that's going to be the greatest when sine t, the absolute value of it, is equal to 1. So in other words, when regular sine t is 1 or -1, that'll basically give us a velocity of, or a speed of 4, because our velocity would be +4 or -4. Well, that is going to occur at the same times that cosine is 0. So in other words, looking here and here, those are the spots where the sine graph is either at a maximum or a minimum, which that was our velocity, which its absolute value is its speed. The reason that's interesting is that means the spring, the weight on the spring is moving its fastest as it passes the equilibrium point of position 0. And its speed will be 0 anytime sine is equal to 0. Well, this is when the cosine graph is at its highest and lowest points. And that kind of makes sense. It'll be have a speed of 0 for an instant when it reaches either +4 or -4 when it goes to change directions. So we're going to see if we can use our sine and cosine derivatives to find the 27th derivative of cos x. Well, we know the first derivative of cos x would be -sine x. The second derivative would be -cos x. The third derivative would be back to +sine x. And then for the fourth derivative, we're back to +cos x. So notice it's a cycle of 4. So every multiple of 4 then would return to cos x. That means that our 24th derivative must be cos x, because it's a multiple of 4. That means that our 25th derivative must be -sine x. Our 26th derivative must be a -cos x. And making the derivative we want, our 27th derivative, a +sine x. So because it cycles, we can figure out any derivative way down the line. It's kind of like back in trig when you did i's, how I to the 4th was equal to 1, and you were able to figure out I to any huge power because it cycles through. So getting back to the limits, which I mentioned before, we saw that if the inside of our sine matched what was in the denominator, that limit was just equal to 1. Well, that's going to be our goal here. We have a 7x on the inside of our sine. We want a 7x in the denominator, so we've got to somehow make some adjustments. So we need to think about what do we need to multiply the 4x by in the denominator in order to make it a 7x. Well, the thing we would need is to multiply by 7/4. But you can't just throw a 7/4 in the denominator and do nothing else. We need to keep it the same value as it was before, so we've also got to throw a 7/4 in the numerator. Now, because that 7/4 won't be affected by x, we can throw it in the numerator out front. So if we rewrite this, really what we'll have 7/4, which is the one that's out front, times the limit as x approaches 0 of sine 7x, now over 7x. Well, this will be 7/4 times, we know this just has a limit of 1, so we'll end up just getting 7/4. And we can make that adjustment regardless of what's in that denominator. As long as we got the x part in there, we can just multiply top and bottom by a constant to get what we need to match it up. Working with some limits again, we've got the limit as x approaches 0 of x times cotangent x. Well, we can write cotangent x as sine x over cos x, or sorry, cos x over sine x, reverse of that. And I'm going to show you two ways you can think about working with this. The first is, let's think about this as two separate limits. The limit as x approaches 0 of x times cos x over the limit as x approaches 0 of sine x. And we can do that as long as the limit as x approaches 0 of sine x exists. Well, to get what we've been working with before, we want this to be a sine x over x, so it's something that we know how to work with. So let's multiply the denominator by 1 over x. Well, if you multiply the denominator by 1 over x, you've got to multiply the numerator by 1 over x. And now let's neaten this up. We've got the limit as x approaches 0. X times cos x times 1 over x will just be cos x. And this will give us sine x over x. Well, the limit as x approaches 0 of cos x, that's something we can do direct substitution with. When you plug in 0 to cos x, you just get back 1. And in the denominator, we know the limit as x approaches 0 of sine x over x is just 1. So in the end, this will just give us 1. Now, an alternative way we could have approached this is we could have done this as the limit as x approaches 0 of x over sine x times the limit as x approaches 0 of cos x. So all I did was I put the sine x under the x rather than under the cos x. Well, if the limit of x as x approaches 0 of sine x over x is 1, because 1's reciprocal is just itself, the limit as x approaches 0 of x over sine x must also be 1. Okay, and again, that's only because 1 is its own reciprocal. And then we just saw a second ago we could do direct substitution with that right-hand limit, so therefore this would give us 1 as well. That's a second way we could have approached this. That's all for today's video. We'll see you next class period.